Good morning or good afternoon, depending on where you are at. My name is Atarot Azizi Namini, Director of the ABC UTC. We've got some more detailed news about the upcoming 2021 virtual ABC conference. Registration is open. The conference is between 8 and 10, Wednesday, Thursday, Friday. This slide shows you the co-sponsoring state DOTs that are co-sponsoring the conference. 30 state DOT, FHWA, TRB. We also have the Uhbc as a co-sponsor of the conference. We are very delighted to tell you that we have two congressmen that are good friends of the bridge engineering and very much involved with the transportation. A member of the committees on transportation tech Congress. They're going to be with us. They're confirmed. Will be sharing their thoughts with us. And we'll be making some remarks during the conference. The welcoming group also includes Carmen Swanwick, the chair of the AASHTO Cubs. And we are also delighted to have a speaker from the US DOT, Firas Ibrahim, a very good bridge engineer himself, and to provide us some of his thoughts on the ABC and so on. We also have several keynote talks with the speakers from around the world to provide us with an opportunity to learn from the latest development in ABC in other countries. You can go to our website and see their names, the title, and affiliation. We have speakers from Switzerland, from Sweden, from China, from Germany, from England, from Holland. We also have select keynote speakers that we selected to provide not only to us in the US, but also to the rest of the world on what we do in the area of the ABC in the US. And you see their names. They don't need any introduction by me. So there are 8 US keynote speakers in total, as you see here. The conference also includes the award program that is chaired by Ahmad Abu Hash. And how to submit your nomination. Now, these projects have to be outside the US. So if you go to our website, you can see all the details, the forms, how you submit them. And please remember, October 8, 2021 is the deadline to submit your nominations. The conference includes the Uhbc workshop. It's going to be hybrid. It's going to be very interesting. There will be reception on Wednesday. Also, there is a very good opportunity to exhibit, to showcase your service, and also have a sponsorship. So the name of the companies or the company that will be sponsoring will be shown during the presentations and different points during the conference. If you are interested to exhibit or be conference sponsor, please go to our website. There's an email that you can contact. In a glance, so the conference program is going to be finalized by September 27. In addition to all the keynote speaks that I mentioned, there will be 30 additional presentation based on the abstract that we received. There will be one presentation at a time. There will be no concurrent. We've done something very interesting. Engineers think more than just the engineering concept. And so in between the presentation, we will have a music spotlight that's going to present the music of the world, different countries that are participating in the conference. In between presentation, we are also going to have short spotlight on our sponsors and the exhibitors. Uhbc workshop, as I mentioned, award program, reception, and of course the exhibit.
Our presentation today features Idaho's ABC multi-span bridge over the Snake River Replacement Project. We're pleased to welcome our presenters, Matt Farrar, State Bridge Engineer with the Idaho Transportation Department, and Shane Brown, Senior Engineer with Parametrics, Inc. Matt?
Thank you, Mary Lou. Thank you for that introduction. I'd like to thank FIU and ABC UTC Advisory Board for the invitation to speak on ABC in Idaho today. Early on, the Idaho Transportation Department saw that there could be big benefits in using accelerated bridge construction. Starting around 2008, we have let for contract for the use of SPMTs and precast pier caps and precast piers for a project that we had on the Interstate I-84. We then progressed to entire bridges constructed from prefabricated bridge element systems, precast abutments, precast piers, precast pre-stressed decked girders, connected with Uhbc. In 2014, we did our first bridge slide. That was in a design build contract, and that was followed up with another bridge slide in 2020 on I-84, and that was a design bid build contract. Also in 2014, we utilized full depth deck panels. And finally, we recently piloted a project for construction with the use of steel I-girders with cast in place concrete deck in segments, and those were cast off site, and then we craned those into final position and connected them with closure pours. In summary, Idaho has been using ABC concepts for about 50 projects that we have had underway. And Idaho's use of ABC has been very positive, and we will continue to use ABC as a tool in our toolbox. I'd like to introduce Shane Brown from Parametrics. Shane is going to talk about the State Highway 51 bridge over the Snake River. Shane's firm, Parametrics, and Shane were good enough to join us on the design of this project. And Shane, take it away.
Thank you very much, Matt. I'd also like to thank ABC and UTC for this opportunity to present our featured project for today. So today we're talking about the State Highway 51 over Snake River Bridge. I'll give you a description of the project, design challenges, the solutions to those challenges, some details on the superstructure design and substructure design, and then also what everybody likes to see, the construction. Contributors for the project included the people you see here. ITD did the majority of the roadway civil design, and also did the early on design the TSNL to select the type size bridge replacement that we're going to talk about today. ITD hired Parametrics after they did the TSNL to complete the design and take it all the way through PS&E. American Geotechnics was the geotechnical engineer providing the foundation design. Forrester and Associates provided hydraulic and scour design. And then the contractor was Cannon Builders. And then the precaster was Forterra. And Lafarge Duckel provided the Uhbc for the connections. Nucor and Skyline provided the steel pipe piles that we'll be talking about today. HLE was the contractor's engineer who did all of the construction engineering. And then Western States Rebar provided reinforcement, and of course FlexiFloat, which you'll see their product being used here in the presentation for the barge that was used during construction. The project was the typical design bid build project with 6 bidders. The low bid came in around 6.8 million, with the high bid coming in around 8.8 million. The contract was set up to have 299 calendar days to complete the work, with liquidated damages of 4,100 per day. Construction started in early January 2017. The bridge was opened to 2 lanes in late 2017, and paving was completed in spring of 2018. The project is located in Idaho. Here's a map of the US, and Idaho is in the Great Northwest. And more specifically located in Idaho, we're talking about the southeast corner of Idaho here. And if you want to kind of get another pinpoint here, from Boise, it's an hour southeast to the project site. So heading south on I-84, and then when you get to Mountain Home, you take another south turn on State Highway 51, and eventually you'll get to the project site. In this photo, you can see here, State Highway 51 runs north-south across the river. This is the Snake River. It's actually being, there's a reservoir here, CJ Strike Reservoir, with the dam right here. The bridge is actually just in the eastern limits of the backwater from the reservoir. Also nearby is the Bruno Dunes State Park, a great place for recreational people who like to play in dunes. And then, as you can see, lots of agriculture in the area. So State Highway 51 plays a valuable link for especially the agriculture, a lot of the product that needs to get to market. So the existing bridge was built in 1958. It's a 19-span precast stringer with cast-in-place deck bridge. The substructure consisted of pile bent substructure type, so 4 piles per bent with a cast-in-place cap. And then the deck itself, the surface, was a two-lane bridge with minimal shoulders and of course substandard rails with today's standards. But the real purpose for replacing the bridge was due to the issues that you see here. On the left is a picture of the existing stringers. They were framed into some cast-in-place end diaphragms, but unfortunately, inspection reports identified in the early 90s, or mid 90s actually, that there was starting to become significant cracking at the ends of these members. And so lots of deterioration started to occur over time, including significant spalling at the ends, which was opening up opportunities for corrosion for the reinforcement inside the members. ITD throughout the years had been working to extend the service life of the bridge by installing these steel brackets to the face of the pile caps. So here on the left-hand side, you can see a location on the existing bridge where there's a tower bent, where it's 2 bent side by side, and then you can see the steel brackets that were being installed to help extend the service life of the bridge. But recent inspections had identified that even the steel brackets were starting to show signs of significant deformation. So ITD had made the decision that it was time to go ahead and replace the bridge. So challenges with this bridge replacement, of course, we want to minimize impacts to the river. It was determined that we needed to maintain 1 lane of traffic at all times and limit construction to a year. So minimizing impacts to the river, here in this Google image, you can see this is State Highway 51 right here. On either side of the highway, you can see the river and the wetlands that would be associated with these types of crossings. So the decision was made early on to avoid realigning State Highway 51 and to go ahead and utilize stage construction in order to maintain the same horizontal alignment. We also wanted to reduce the number of piles that were going to be installed in the river. So the stage construction, there was really 3 stages. This is a view of the existing bridge that you already saw a picture of. Again, a 2-lane bridge, minimal shoulders, minimal rail today with today's standards. The bridge was built in 3 stages. First stage, stage 1, we built just part of the bridge. And then in stage 2, we shifted the traffic over a single lane. And then in stage 3, we connected them with the closure pour. The traffic control was maintained with temporary signals at each end. Here's a picture of the temporary signals that we used. The traffic volume, it's not a very high traffic volume, which is why these single lane closures work like this. The one directional ADT was 575 with only about 6.5% trucks. To limit the construction to a single year, we looked to many options, but what we fell on was utilizing deck bolt T-girders with ultra high performance concrete, provide an asphalt overlay with spray applied waterproofing membrane, and then for the rail, use a 2-tube curb mount rail. So here in the picture, you can see the deck bolt Ts. These deck bolt Ts were connected with ultra high performance concrete between each girder. The overlay shown here varied from 7 inches at the abutments and piers to just a little over 2¼ inches minimum at midspan. And then here's the 2-tube curb mount rail. Benefits of the selected superstructure were really, it eliminated the cast-in-place deck, saving approximately 4 months of work, figuring about 2 months for each stage of construction. The asphalt overlay was also faster to construct than a concrete overlay, and the rail type provides a better view of the scenic river. Focusing on the substructure and what we could do to help expedite the construction process. This is a fairly long bridge, so we had to do some extensive calculations to make sure integral abutments were appropriate, but it was determined that integral abutments are acceptable for the bridge length, and it was founded on a single row of steel H piles with a cast in place pile cap, and then of course the end diaphragm right here. With regard to the piers and the water, we went ahead and elected to use a cast in place cap beam founded on top of pipe piles, 4 36-inch diameter pipe piles with a 1-inch wall. Benefits of the selected substructure included a significant reduction in in-water work time. We didn't have coffer dams, drilled shafts. We don't have pile groups with a cast in place pile cap to construct, and there were no cast in place or precast columns to construct. It also reduced environmental impacts to the river. It had a higher reliability to the capacity of the steel piles with the use of pile dynamic testing. And ultimately, we provided a jointless bridge deck, so reduced maintenance costs in the long run. So more specifically about the superstructure design, the precast girders themselves, like I mentioned before, were connected with ultra high performance concrete. For most of us who've been listening to these webinars in the past, we've heard about ultra high performance concrete. There may be some that have not heard about it, might be new to bridge engineering, so I'll talk a little bit about it. All the design was completed using this tech note, Design and Construction of Field Cast Ultra High Performance Concrete Connections. It's a FHWA publication. The publication number is there for you. And FHWA's contact Ben Grable, who really authored this publication. He's a great resource if anybody's interested in learning more about it. I highly recommend you pick up this tech note and read through it. And if you got questions, give Ben a call. Ben, I personally called twice during the design of this project just to get confirmation of the information that was in here and make sure I was applying things correctly. So ultra high performance concrete is really a composite material. It includes Portland cement and supplementary materials like silica fume, fly ash, or slag. Uses fine aggregate, not coarse aggregate. Has chemical admixtures like accelerators and superplasticizers. Of course, uses water. And then another key ingredient is the steel fiber reinforcement that goes in this material. The steel fiber reinforcement is typically about 2% by volume, and it consists of little half-inch steel fibers, half-inch long steel fibers that are about 8/1000ths of an inch in diameter. So why did we elect to use ultra high performance concrete for the girder flange connection on this project? Well, it has a high tensile strength. It's self-consolidating, so it's easy to flow into the keyways and around the reinforcement. It bonds well to the precast surfaces when it's prepped accordingly. It has a high durability and low porosity, which is good for our freeze-thaw conditions. And it has a short development lap splice length, which is really beneficial. In particular, the reinforcement lap splice in the ultra high performance concrete, the information for lap splice and development length are provided here. So depending on your cover requirements, you'll see that your development length is anywhere between 8 and 10 bar diameters. And the more unusual piece of this, I think, when people first start working with this is the lap splice length is only 75% of the bar development length. For us in bridge engineering or any concrete design really, that's an unusual thing to hear, that your lap splice length is shorter than your development length. What we typically see using just regular reinforcement and regular concrete is we see our lap splice length about 30% longer than our development length in today's codes. So this was one area where I actually contacted Ben Grable to ask for clarification to make sure I was understanding the information correct in the tech note. Ben assured me that I am interpreting it correctly, that there's been plenty of research done to show that the bars, when tested, actually they break inside the precast and not inside the ultra high performance concrete. So he's got lots of data to support these recommendations, and so we followed them. So for our particular project, the way we connected our girders together at the keyways is we used a 6-inch wide keyway that accommodated a 4-inch non-contact lap splice. All of the reinforcement in the flange was epoxy coated reinforcement. The top mat were number 5 bars and the bottom mat were number 4 bars. As I mentioned before, the Uhbc concrete bonds well to the existing precast surface if it's prepped correctly. The best way to prep it correctly is you need to get an exposed aggregate finish on the inside face of that keyway. And a good good way to do so is to use a retarder on the form, and then when they cast the member and remove it from the form, they go ahead and power wash it and expose that aggregate, and it gives a nice exposed aggregate for that UHPC material to bond to. Here in this picture, you can see stage 1 on the left-hand side and stage 2 construction on the right-hand side. On the left-hand side, you can see the UHPC keyways filled between the girders, and on the right-hand side, of course, you can see the UHPC is not in the keyway, and you can see the exposed epoxy-coated reinforcement. More specific about the pre-stressed deck bolt T-girder design, we utilized 67-inch deep deck bolt T-girders with the 8-inch thick top flange. It used 6/10 270 KSI low relaxation strand. All other reinforcement was A615 grade 60, and the concrete at release was 7.2 KSI, and at 28 days 10 KSI. The girders were designed as simple span beams with mild reinforcement in the top flange to control cracking at the piers. Dead loads were applied prior to the UHPC keyways as distributed based on tributary area to the girders. So basically anything that would be on a conventional non-composite or a composite deck girder system, anything that's non-composite went tributary to the girders. Similarly, we treated all loads that were applied after the UHPC keyway was installed and cured. We distributed all dead loads equally to the girders. Our live load distribution factors, because this is a new technology that's being used, it isn't like really clear or specifically addressed at the time in the bridge AASHTO LRFT bridge design specifications on what live load distribution factor to use. So we elected to use the worst case scenario, assuming that the girders are connected to act as a unit, and then also not sufficiently connected to act as a unit, so that we could bracket the range of possibility here. Make sure that we're not going to be light anywhere. So more specific about the connection over the piers, like I said, the reinforcement was really designed to control cracking over the piers. So our top flange reinforcement consisted of number 7s in the top and bottom mat of the girder. These number 7s from left and right side of the pier were actually staggered to avoid each other and then have a non-contact lap splice right over the pier. To help with development length, we actually required in the contract plans that a construction joint be formed right here, and that the contractor could come back and pour this the following day, so that you don't have more than 12 inches of fresh concrete below the reinforcement. The reinforcement was really designed, like I said, to control cracking over the pier. So this reinforcement was really checked for the service 1 limit state and not strength limit state. The girders were designed as simply supported for the strength limit state and service limit state, but then also checked at the service limit state to control cracking over the pier. Furthermore, to connect the superstructure to the substructure, we provided dowels that ran right down the center line of the pier that connected these two, along with a keyway. A pretty common detail that's used in Idaho. Location of the bents was also a critical feature for this. The existing bridge was composed of 19 spans, but 3 of those spans are really short spans in these locations right here that actually produce what's called a tower bent. At least that's how it's identified in the existing plans. So the tower bent with those short spans really became an ideal location to place our new piers, which is what's shown in red. So the piers were spaced right between those tower bents, with the thought that the contractor could possibly use the existing bridge to mobilize out on, drive his pile, so remove that short span, then drive his pile, and then work back off the bridge deck. And that's exactly what the contractor elected to do during construction. So here in this photo, you see the contractor's crane out on the existing bridge during stage 1 construction. Stage 1 traffic is over on this side. And here you see the existing tower bents. Another benefit about selecting the location here and making use of the tower bents is the contractor was able to use a steel template to make sure that he had the correct alignment for his piles while driving it through this water column and down into the stream bed mud. So the contractor made great use of the existing bridge to facilitate his tolerances and placement of the piles. More about the pier bent piles themselves. For the foundation, it was decided actually by working with American Geotechnics, the geotechnical engineer, to use 36-inch pipe piles. It's really called a composite pile with respect to the geotechnical world, at least what I learned for the first time on this project, because it's driven as an open-ended pile in the beginning. So the pile at the tip has no closure plate. It was driven open-ended for the first 55 or 60 feet, depending on what pier you're at. And then there was a closure plate that was installed in the pile. This closure plate, once it became in contact with the pile, forced a situation where the pile was then plugged and you had an end-bearing pile. So they call it a composite pile in the geotechnical world because it's first driven open-ended and then forced to have a plug. I thought that was an interesting thing that I learned from the geotech on this project. Beyond the closure plate, the pile remained unfilled with concrete except for a plug that was added to the top. The reason why a plug was added here was the closure plate actually had an 8-inch diameter center hole in it. This allowed water to dissipate from inside the pile, allow the pile to advance down to the stream bed so that the closure plate could come in contact with the stream bed and actually force the plug. To provide corrosion protection for the pile, the upper part of the pile was actually painted with a inorganic zinc paint. The pile were driven to achieve a nominal capacity of 1,550 kips. That was achieved by first, like I said, driving open-ended the first 55 or 60 feet till the closure plate came in contact with the stream bed down below. You could see that you were able to observe that right away in the field because the hammer height would dramatically change as they're driving the pile. And then they were forced to drive the pile an additional 3 feet after it came in contact with the after the closure plate came in contact with the stream bed. That would complete the end of initial driving. The contractor was actually required to do dynamic pile testing and confirm with cap WAP analysis. And if the driving did not achieve, at the end of initial driving, if it did not achieve the required nominal capacity, the contractor was actually required to wait 2 days for pile setup and then retest the pile. All the piles came to capacity after having to do a two-day setup. They did have to do the 2-day setup, but it was good that we got the capacity that we needed because 1,550 kips is not a small capacity to confirm. In addition, there was only really one splice here, one weld to be performed here, and that was at the closure plate. We did provide a detail for an optional splice if had to, but fortunately none of the piles needed to have a splice in this upper painted zone, so we have a good pile corrosion protection still on the pile. So substructure design criteria. So people might be asking, why didn't we fill the pile with concrete, or why did we elect this foundation type? Well, you know, seismic is an important feature to consider, and this bridge is actually in seismic performance zone 1. And in accordance with the AASHTO LRFD bridge design specifications, when you're in zone 1, no seismic analysis is required. And also, the substructure needs to be designed so that you have the minimum horizontal connection force of 25% of the tributary dead load to the support, which is the design process that we took to design the bridge for seismic. Other loads that were applicable for the substructure design included the uniform temperature change, specifically of the superstructure. And then, of course, we have a non-navigable waterway, so that was nice. And then water pressure with a debris raft was also considered. Wind loads, and then connection at the pile to the bank cap designed to develop full plastic moment was elected. We wanted to make sure that that pile was embedded to develop that full plastic moment of the pile into the cap beam so that we had a good connection there. And then, of course, the dead and live lead reactions from the superstructure. So in order to get full plastic moment capacity of that pile inside our bank cap here, we actually designed a very robust group of reinforcement that confined the concrete around the pile. And what you see in these red lines here, these are actually U-shaped bars crisscrossing across the pile in opposite direction. And then these green shaped bars right here, kind of like a top hat bar that help to transfer all axial load into the cap beam. Another view here to help see it, in this section over here on the right-hand side, you can see our red bars and kind of highlight them here in red. These were, again, those opposing U-shaped bars. And then, of course, we had the additional number 8 top hat bars that I like to refer to them as. And then, of course, in plan view, just to help kind of see the whole picture, here's those U bars tied in, and then, of course, the top hat bars right there. So, beyond design, let's talk a little bit about the construction. So the contractor started with stage 1 construction, started with demoing out those tower span, short tower span, and then demoing out part of the bridge itself. He worked with 2 cranes, as you can see here in this picture. So on the right-hand side, the contractor's crane is mobilized with this hammer, and he's actually driving pile. On the left-hand side, you can see a pile sticking up in the air. And waiting to be driven down. So the contractor worked back and forth this way on the existing bridge while traffic was on the other side of the bridge during stage 1. Here's another picture of the pile driving that was done by the contractor. As you can see here, that this beam right here, there's actually a steel bracket here. As we mentioned, the bridge was being replaced because there was some deterioration at the ends of the beams that were causing, issues with bearing at the ends of the beams. So as part of the construction, we required the contractor, if he mobilized construction equipment out there, to provide design calculations that show that the beam can handle it with the existing brackets that are out there that were supporting the beams. Since construction loads are often heavier than highway loads. And during design, we did do a load rating of the bridge to verify that the stage 1, situation with reduced number of stringers was satisfied with the additional weight of the temporary barrier that was installed. The load rating was acceptable for the bridge for highway loads, but for construction loads being much higher, it was not acceptable. So the contractor had to do a little extra work to design this little bracket, and he applied those anywhere where there was signs of deterioration on the bridge where these brackets were installed by ITD to help extend the service life of the bridge. So it worked very well, actually, and it made it possible for the contractor to take use of the existing bridge for construction for driving these piles. Here's a picture again of stage 1 construction showing the cast in place cap is complete after the pile driving was done. And you can see dowels sticking out to make that connection to the superstructure. Here in this picture, you can see that after the pier caps are done and the abutment was complete at the ends here, the contractor went ahead and mobilized his crane out onto a barge. In fact, all construction was performed for this bridge working off of barges for the contractor. No temporary structures like a temporary platform with piles driven into the river was utilized. All work was performed off of barges. So the contractor, when he was ready to erect his girders, went ahead and mobilized his crane in, as you see here in the picture. And then the truck comes in, he goes ahead and connects his crane leads up to the pick points on the girder, a single crane to pick this large girder. And then he just started to proceed with the girder erection, as you see here. So what you see here is stage 1. First girder is erected, the exterior girder. Now his first interior girder is coming to land on the bearing pad. Once the girders were erected, the contractor was ready to start installing the ultra high performance concrete. Here's a picture of the equipment that was used to place the ultra high performance concrete. All batching of this material was done on site. Here's some more pictures about the UHPC placement. In order to place this material, the contractor has to form on the bottom side, but he also has to put a form on the top side because this material is so flowable with the superplasticizers and additives in it that once it starts flowing, it flows really well. In fact, it actually flows up and out of the form, especially in low spots. So pre-stressed girders tend to camber up, and so at the ends of the girders would be the low spots, and this material really would start to flow out of it. Plus, the specifications for the project really required that the the UHPC flow about 1/4 of an inch up out of the joint, and then the contractor has to grind the joint flush with the deck after it's cured. So in this picture, you see the crews installing the forms across the top over that. And then in this picture, you can see the material flowing as being placed. The apparatus used for pouring the UHPC was pretty simple. They referred to it as the bucket on site. So pretty easy to place the material. They mix it and place it in here, and it just makes sure it flows directly into the keyway. You can also see in the picture, again, the epoxy coated reinforcement. The prepped keyway might be hard to see, but there is an exposed aggregate finish on the keyway, and the material's flowing. They need to get some more in here soon, though. After the keyways were poured, the contractor then had to grind the keyways, as I mentioned before. So what you see here on the left-hand side is this keyway has already been grinded, so it's flush with the adjacent girder flanges. And this keyway grinding is taking place as we see right here. So stage 1 is complete in this picture here. On the left-hand side, there's the 2-tube curb mount rail, of course the keyways, and then of course the girders and the temporary barrier. On the right-hand side in the picture, you see stage 2 construction in progress. The contractor's got his dual cranes out there. He's got equipment out there. You can see a pile up in the air right here as he's working to drive his pile and demo out the bridge working back from center. Here's a picture of stage 2 demolition, the contractor's crane on the existing bridge picking the rail right now. Again, work being done off barges. And then stage 2 construction really proceeded along the same lines as stage 1. Drive your piles, construct your caps, place your girders, and do your intermediate diaphragms, and then do your UHPC keyways. So here you see an aerial view of stage 2 with the barge mobilized and ready for the girder erection already. Stage 2 girder erection proceeding. As I mentioned, lots of agricultural product comes out of the region here. So you see, I believe these are Idaho's famous potatoes crossing the bridge. And of course, you know, the first 2 girder lines are installed and crews sitting there waiting to make sure that the girders land on the bearings correctly. Some of the key things about these ultra high performance concrete keyways here, because there's tight tolerances on the lap splice length, you know, we're only asking for a 4-inch lap splice length, but you have to have some good control over tolerances. And these girders, pre-stress girders, naturally have a sweep in them, and the tolerable sweep is usually around 1/8 of an inch per 10 feet. Now these girder span lengths were around 157 feet, so you're talking almost 2 inches of sweep that could have been allowed in a girder per tolerance from PCI. But that wouldn't have been acceptable with these keyways, because these keyways are, you know, only 6 inches wide, and we have a non-contact lap splice of 4 inches. So the contract plans actually required the contractor to provide a method to correct girder sweep. In addition, the contract plans also required the contractor to provide a method to correct differential camber between the girders, especially since these keyways are going to be grinded flush with the adjacent girder flanges after they're poured with the UHPC keyway. We wanted to make sure everything was leveled up transversely and everything was spaced accordingly for the keyways to get the required non-contact lap of 4 inches for the reinforcement. So the contractor utilized a come-along system to correct the girder sweep, and some wood spacers that were cut to be 6 inches wide, so that when he pulled the girders together with the come-along, he made sure that he didn't, you know, go too much, and he came right to the exact spacing of 6 inches. The system worked really well. I was really happy with it. During design, I reached out to fabricators, like Matt Farrar and myself actually reached out to fabricators to confirm, you know, the tolerances and girder sweep and you know, methods that could be used to correct these girder sweeps, so that we can make sure that we had a solid system that was constructible. Those meetings paid off. It was good to hear from fabricators. I highly recommend anytime you're using a new system, or even just starting a new bridge, it's good to talk to the local fabricators, see what's the latest trends, learn what's going on in the industry. To correct the girder camber, the contractor utilized some strong backs, some steel beams on the top and bottom below the beams, and just some simple tie rods to go through the girder flange, between the keyways here, between the girder flanges, and then he just tightened those up so that he could suck the girders together and come in alignment. So the bridge is complete. This is a picture of a side view from the north bank. This, as you can see here, all the existing piles have been removed. It's nice 4-span bridge. It's been opened up for the boaters. One might ask, what are these things on the ends of the bridge here, on the ends of the piers? Well, they're actually vertical gauge signs. They inform the boaters of the low clearance underneath the bridge. This project was a little unique because we typically have to raise the profile of bridges to provide vertical clearance, but because this river is a non-navigable river, there was no vertical clearance requirements with regards to that. However, it is a boater friendly site. A lot of boaters come out here to enjoy the facility. So there was a small profile shift, but there was also a small drop in the vertical clearance for the compared to the existing bridge. Not a significant one, but it was enough that the Coast Guard still wanted us to sign the bridge for the vertical clearance to inform boaters of the low chord clearance that's underneath the bridge. So some lessons learned, one of the things that happened during construction was forms needed to be secured tightly. There was one instance where material had blew out, but it got corrected quickly. Need to keep good head pressure on the bucket to ensure full placement of the UHPC and the keyway. There was a place where it ended up being a little low and didn't reach the 1/4 inch over the top of the flange. Experience helps to ensure a timely execution of work. This is new construction methods being used. It's not brand new, but it's new to many of the contractors, and so there's always a learning curve. And of course, the UHPC material actually costs money, so you want to detail to minimize how much of it you're using, which is why we focused a lot on the width of the keyways. So at this point in time, I think I will open it up for questions.
All right, thank you, Sean, for a great presentation. At this point, we're going to turn it to Paul Lyles and Ahmed Abu Haj to moderate the question and answer period. Paul?
Thank you, Torrid, and everyone, and Matt and Shane. That was really a good presentation. We do have a number of questions that came in before the presentation, and we also have some questions that came in during the presentation. So we'll go ahead and get into that. The questions have been broken into design questions and construction questions and maybe a cost question. But anyway, the first question I have was, can you define the decision-making process, guidelines, cost estimates, and comparison scoring metrics, etc., to reach an ABC recommendation?
Yeah, Paul, this is Matt. I'll take that question. That's a very interesting question, a very good question. We have considered establishing guidelines for the use of ABC, but Idaho is a fairly small state, but and we have fairly low ADTs generally throughout the state, and so traffic is not really driving our decision-making process, but speed of construction and shortening detours, those really drive what we're trying to accomplish. And so in the type, size, and location portion of the project, we always have a consideration for the use of ABC. And we've always found that the traveling public, we get very positive comments from them if we get projects done quick and early, no matter whether it's out in rural Idaho or right along our interstates in Boise. So we always consider ABC practically for every project that we've got. We don't like to be tied down so much to rigid guidelines, and so we evaluate that on a case-by-case basis for every project.
Okay. There was a question that came in during the question and answers. Pretty easy, I think. What code book was used in the design?
Yes, that was the AASHTO LRFD Bridge Design Specifications, the 7th edition.
Okay, and you used the HL93 truck loading?
Yes, HL93.
Okay. The next question was, this came in beforehand, was there any permitting requirements that created challenges for use of the ABC methods?
None that I'm aware of.
Okay. The next one, this gets into the construction, analysis. Were there any permitting requirements that created, did the engineer of record evaluate the construction loads on the existing structure? Or did the contractor's specialty engineer perform the analysis?
So during design, I mentioned in the presentation that we analyzed the bridge for the reduced width to accommodate the single lane for highway vehicles. The bridge rated out okay for the highway vehicles, which was why it was acceptable to utilize the stage construction that we did, but we did not analyze the construction loads from the contractor. It's really hard to know for sure what the contractor's loads are, but we did require that the contractor self-perform that engineering and submit that for our review. So if you wanted to have equipment on the bridge, you needed to provide calculations that showed that the bridge was safe to handle that equipment. And in particular, we really required the contractor to meet a operating level safety like you do with load rating, where you had to have a satisfactory operating rating level of at least 1.0, which means for his construction live loads, he was using a load factor of 1.3.
Okay. Did the plans contain the suggested staging sequence, or did the contractor develop or modify the staging sequence any?
The plans did have a staging sequence in the plans. Yeah, so, but the contractor also requested to modify it a little bit. We've reviewed his request and made some exceptions to change it, but not a lot changed.
Okay. There was a question that came in during the presentation. It says, did you take any steps maybe to limit differential deflections or vibrations when the two separate structures, between the two separate structures while the Uhbc cured in the closure pour?
That's a very good question. Thanks for asking. Yes, there were some measures that we tried to take. Okay, so in the stage construction here, for stage one, of course, 3 girders was carrying the live load. The reason why we shifted the traffic a third time is because we wanted to try to do the best we could to minimize the vibrations here. What we did in order to do that was the contractor was required to install the intermediate diaphragms between the girders. We didn't talk about that much in the presentation at all. So after they erected the girders, went ahead and did the girder camber equalization and also corrected for the sweep, the contractor then installed his permanent intermediate diaphragms between all the girders. That then helped lock the girders in. He went in and poured his keyway, and then he shifted his traffic over here. We were trying to get as many girders as possible participating in this so that we don't have as much differential vibration between the two stages. That was the best that we could really do.
Okay. Leave that slide up. There were some questions here that came in about the overhang. How was the overhang designed, and is the barrier wall integral with the exterior beam with the TL rating?
So this is a 2-tube curb mount rail. The overhang for the girder was designed to accommodate, because it is a 2-tube curb mount rail here, full plastic moment of the post itself, and then of course the lateral load applied at the top rail in accordance with the bridge design specifications, the AASHTO LRFD bridge design specifications. So the reinforcement was designed pretty much just like your regular conventional overhang for these girders.
Okay, is the rail crash tested?
The rail crash tested. This is a, this is a rail that's used in Oregon and in Idaho. I'd have to go look up the exact crash test level. I think it was a 3 or
Okay.
4. I don't remember off the top of my head. I'd have to get back to you on that one and
All
tell
right,
you what
okay.
the crash test level was.
Hey, Paul, I could
Yeah.
add in there, this bridge was designed prior to the MASH crash testing requirements, so I think it's an NCHRP 350 crash tested rail.
Okay.
Thank you, Matt.
All right. We have a question here. Was stainless steel considered for the top steel and steel over the piers?
No.
Okay. Then the next question I have is, was lightweight concrete considered to reduce the weight of the deck girders for hauling and erection?
It was not considered. It's a good question, but no, it was not considered during design. Matt, did you guys ever consider that at the TS&L level and we just didn't talk about it? I don't recall talking about that.
Yes, we did think about that a little bit. We have a practice of what we call counter cambering the girder, and that's where we thicken the slab to account for the camber that's going to result, so the bridge deck comes out flat essentially. And that additional weight is quite a bit. And so we were thinking about lightweight concrete in this solution, but after looking at all the various aspects of getting the lightweight aggregate up here to Idaho, we decided to just go with normal weight concrete, and we did not counter camber these girders.
Okay.
Thank you.
There was a question that came in beforehand, and you discussed it pretty well. I think slide 29. Can you discuss the details of the girder and deck longitudinal connections over the piers? You discussed this pretty thoroughly. I don't know if you want to add anything to it. I think you did it pretty good.
Yeah, I think I covered this one pretty good.
Okay. Then the next question, how did the contractor attach the form tops to the deck to protect flow out of the UHBC?
To the top of the deck?
Mm-hmm.
That,
and the
that's
bottom
good.
for that matter.
Yeah. And you know, I'd have to get back to that one and pull open the submittals. I don't remember the exact method he used. Yeah, I don't remember the exact method.
All right, that's fine.
Did you have something?
Shane, typically I could add that in the bottom of the top slab of the deck bulb T, we have the precaster put inserts in to attach the plywood form on the bottom. And that's kind of a similar attachment that we have for the top form as well.
Okay. We've got a few questions here on piling. The first one, what was the average depth of the river channel at the bridge?
Well, as far as the water depth was going, it was about 20 to 15 feet.
Okay. Then in the piles, it says, how were the piles in the splash zone protected from corrosion? I think you kind of mentioned this. Was that on the inside too?
No, it was only on the outside.
Okay. They asked the question beforehand about, can you provide information on the design and construction of the pile vents? And were there any consideration for long-term corrosion? I think you've covered that pretty well in your description of the pile and then on the zinc protection. So we'll go on from that one. Let's look at another one that on the piles. Could you discuss the choice of steel versus pre-stressed piles in the vents? Were there any substructure obstructions that required pre-boring or exploration?
No, there was no nothing below surface that was anticipated that would require pre-boring to install piles. No consideration was really given to pre-stressed piles. Matt, correct me if I'm wrong here, but pre-stressed piles isn't something that's typically used in Idaho. I'm not even sure that the local fabricators have the ability to fabricate those. Is that correct?
Yes, that's correct. We don't have experience with using precast piles in Idaho.
Okay. a couple questions on construction came in beforehand. Can you discuss the delivery time and temperatures for ultra high performance concrete, and was the UHPC batched on site?
The UHPC was batched on site. What the temperature was, the days that they were placed, I don't know. I don't have those records. But there is a requirement that, you know, if you got cold weather, you still got to treat it kind of like cold weather concreting. Matt, is there anything you want to add to that?
We have used UHPC on very hot days, and we've had issues with that. The UHPC cement and additives are all stored on site on the other jobs, and if the temperature is high, we can really run into some problems when we mix up the UHPC and place it. Contractors have had to use ice and have air-conditioned storage containers in order to avoid those issues.
Okay. There's a question here. This is pretty interesting. It says, what type of cement was used on the project? Particularly cement type 2 MH, which I think stands for medium heat, or cement type 1L parentheses 10. That's where there's something substituted. And what was the class of concrete used on the bridge?
So I'd actually have to get back to you on that one. Typically, it's type 1 or 2 that's specified for your general concrete, your regular structural concrete for like the cast in place piers, and then the pre-stressed girders are typically type 3, the high early strength. But more specific than that, I have to get back to that one.
Okay, we think this has to do with like mass concrete controlling the heat. You didn't have any mass concrete on the job, did you?
No.
Okay. And then there's a question that came in about, were there any claims from the contractor about ABC construction for the project?
That I don't have the answer to. I don't know if there were any claims. It was not brought to my attention that there were any. Matt, do you know of any?
No, I do not. This was a relatively claim-free project. I don't recall. I do remember some issues with the asphalt mix and those kind of things, but not with the bridge construction itself.
Okay. Then final question here. Somebody had asked about the price per cubic yard of the UHPC. Was that a separate bid item?
It was a separate bid item. The UHPC material, the winning contractor, his price was $6,500 per cubic yard. But it ranged all the way up to, and I think he had the low cost per cubic yard for the material. The high was $8,000 per cubic yard. So it ranged between 6.5 or 6,500 to 8,000 per cubic yard from the bids.
Okay, now that was the bid cost, so that's the materials plus the construction for it.
Yes.
Whatever. Okay, that's good. All right, it's 10 after. I'm going to ask Ahmed if any questions have come in during the question and answers, and he will go ahead and see what we got here. Thank you.
Thanks, Paul. Yeah, we do have several questions. One question about the pile cap connection. Did that require additional reinforcing steel?
Yes, that's what I tried to present in the presentation. We actually added a bunch of additional steel at the piles where we had the crisscrossing U-shaped number 9 bars and additional number 8 bars and stuff, the top hat bars that we put in there.
Okay.
The intent was to get full development, the full plastic moment of the pile.
Thanks. There was a question related to the leveling correction. Did you check the stresses that were induced because of the deflection?
So the equalization of the girder cambers, the stress is historically those don't get checked in Idaho. Those typically are assumed that once the system is all connected and composite, that it kind of counterbalances each other out and they act as a unit anyways. Matt, if I've said anything wrong here, please, weigh in here. But specifically on this project, we didn't do stress checks for the camber equalization.
Well, it's a good question, and we have checked those in the past and made sure that we weren't exceeding any kind of tensile cracking stress when we do that.
Okay. There was a question about the pre-stressing strands. Were they epoxy coated?
No, they were not.
Okay. How long were the pipe piles?
So embedded below the stream bed, they were about 55, 60 feet, and then you got another 30 some feet above that. So yeah, they're about 70 feet. Oh, sorry, 60 feet in, and then another 30 feet above that. So you have about 90 feet total length.
Okay. There's a question about welding the top plate to the top of the 36-inch piles.
Yes.
The question, is that a common detail to Idaho or the structural engineer or the geotechnical engineers?
It's common to me. I've used it in many times when I'm trying to reduce the weight of pile. If you're having a situation where you your foundations are exceeded, not exceeded, but limited for axial capacity. So there is a top plate right here, a little fillet weld around the top. The top plate was actually reduced to be 1 inch less than the outside diameter of the pile itself, so that you had a fillet weld right there. This plate doesn't really do much except stop concrete from filling into the pile and just making sure that it transfers, bearing load on top of the pile to the pile. So laterally and stuff, there's really no load really to the weld.
Okay. What design case controlled the bent cap design?
What design case?
Yeah.
Well, like I guess specifically about the bent cap itself.
Yep.
Oh, okay. So of course we obviously checked for the dead and live load on the bent cap. So we definitely, strength limit states, control, but we also imposed those plastic moments from the pile to make sure that the reinforcement in the cap was adequate to take and transfer that load from the pile into the concrete also. So I mean, which one controlled? Vertically, the strength limit state did, but laterally, that plastic moment on the piles controlled.
Okay. Well, it's 1:15. We're running out of time. Torrid?
All right. So we'd like to thank our speakers today. On that note, we will conclude the webinar today and hope to have you with us for next month. So long.